Assalamu alaikum, ladies and gentlemen. This is the chapter number 5 of the GIS course, Geo-Informatics. Previously, we have studied the vector data model and object-oriented data model. And now, although did some we did some study previously regarding this raster data model, and then this is, I think, our second presentation on raster data model. Unlike the vector data model, the raster data model has not changed since the last 30 years, maybe starting from 1990s. Research on raster data model has instead concentrated on data structure and data compression, because whatever file you develop for the raster data or .bmp or JPEG or all that, it takes a lot of space in the computer, or all the satellite imagery or all the scanned documents, they all become part of the raster data actually. So they cover a lot of space in the computer files or the hard disk. So most of the techniques have been developed in the last 10, 15, 20 years how to compress the data and keeping the quality at the same time. So this has been the major research, although the technology or the basic formulation of basic data structure has been the same since a long time. Commercial GIS packages can display raster and vector data simultaneously, like the ARC 10.5 or 10.3, whatever you guys have it. So you will see that both of the satellite data, raster data, I mean from the Google Earth or from the street map, or that you conduct on your own the data digitization, or it can be displayed at the same time. This chapter we are going to divide in 6 parts. Yes, sir. Previously there was one mistake which I have to redo some work. That's why there was a difference anyway. The conversion of models. Following are a few examples of tools which we use in our GIS to convert from raster to, especially if they are points or polyline or polygon, and it can be converted into other kind of data format and within how many types. Let us say raster to point, it is only one, raster to point. And the second one, or the lower one, raster to polyline. This is the line. Contour, stream to feature, raster to polyline, cost path. So this is different type of data which we need. Although we will show the contour will be shown by a line, it is polyline also. Stream or to feature, or raster to polyline, or the path, how much money which we will spend going a certain way. So that is also some sort of a, we have to create some sort of a direction, that is polyline also. Raster to polygon, the area one. So view sheds, watersheds, raster to polygons. So it means these are, if there is a one point and we have to find out how much water will come down to that particular manhole, let us say, or water is coming from one hole, let us say our Westwood colony, and then it comes to only how much water will come down to Raven Road, or to other manhole which we have developed. So this this is raster to polygon. Okay, point to raster, interpolation tools, kriging, splines, density tools, they come point to raster. Polyline to raster. This is also data conversion. Polygon to raster. Polyline is different, polygon is different. Polyline has a length only, while polygon has area, that is whole connected with area. Again, we are showing various kinds of digital elevation models. Resolution 30 meter is the same area, but the pixel size is 30 by 30, 30 by 30, which you are using, let us say, under Google Earth. Or if you go on the net and you try to find out the free without making any payment, uh, most probably you will get 30 by 30 size pixel of the digital elevation model of Pakistan or America. Now the next one, the right side or middle one, is now it is clearer with respect to the left side 30-meter digital elevation model. Now if we go exactly to the extreme right, this is 3 meter, 3 meter by 10 feet, 3 meter digital elevation model. Now here you can find out, you can look down very clearly the deep valleys or deep streams, or maybe the black areas, the high hill, top of the hills, or maybe it is the deep down, it is some sort of canal system, not canal system, the stream system is being developed, or look like you are working, going on GT road and you are looking at Potahar area. So those earthen hills look like this one, but main thing is there is a more clarity, because 3 meter by 3 meter pixel will give you reasonably good idea what type of terrain you are working on. This is from the textbook. Digital elevation model are generally 30 meter, 10 meter, 3 meter and 1 meter. Now 1 meter is very costly. We will not be able to find out that easily from the free market. You have to buy it from Sparco, and Sparco might ask you several questions why you are interested in 1 meter, because the defense agency comes in that why you are asking for so, a higher density, because maybe it is a what is against the it is a security threat. So that is the reason. But even if you have some friends in with the European Union or in India or China, and you can talk to their main suppliers, but they already have done under international protocol, they have made agreements with every country. Whenever they will give this type of 1 meter or maybe 2.5 or 5 meter even, they will ask the defense agency or defense forces of that country, whoever will be the representative of that country. Our Sparco is part of the defense forces. So only they have the ability or the authority to buy the major types of data. The 30 meter and 10 meter DMs are United States DMs. The 3 meter DM is a derived product from LiDAR data. So it means the USGS means that satellite is working. So that is giving enough 30 meter or 10 meter, it is using 30 or 10 meter wide pixel, but if they can interpolate and they have a LiDAR system, maybe then that data will be coming. But I have already explained you that now there is a resolution of 62 or 82 centimeters. I mean less than 1 meter resolution is available now, and it is being sold in the market. Only we have to have the capability or the authority to get that type of data. Thank you. What is raster data? In its simplest form, a raster consists of a matrix of cells or pixels, as you have gone through this book in the chapter number 5, organized into rows and columns like a regular graph paper or a grid, where each cell contains value representing information such as temperature or height. Data stored in a raster format represent real-world phenomena such as thematic data known as discrete like pole, representing features such as land use or soil data. Now, soil data will be continuous data, like a polygon you can say, because 1 acre, 2 acre, 10 acre of sandy soil or clay soil, he's talking about that one. Continuous data representing phenomena such as temperature, elevation, or spectral data such as satellite images and aerial photographs. Pictures such as scan maps or drawings and building photographs. So all of these type of photographs, whichever we have, are the old maps, Survey of Pakistan map, which I have shown you. These will give us, to start with, is raster data. General characteristic of data. What are those special characters, abilities, qualities of raster data, which is not in the vector data? In raster data sets, each cell has a value. Yes. If it is extreme left bottom, that is maybe 0 value, but in raster, maybe the extreme top that has a 0x and 0y. Okay. Number 2, each cell consists of same width and height and is an equal portion of the entire surface represented by the raster. It means whenever we develop a pixel, either it is 1 meter or it is 1 foot or it is 3 meter or 10 meter or 30 meter, whenever we are going to develop the map, raster map, it will have the same dimension. It will be, most of the time, it will be in square shape. So each cell consists of same width and height and is an equal portion of the entire surface. The smaller the cell, the smoother or more detailed the raster will be. 1 meter cell, 1 by 1, and let us say also 1. So if we compare it with 5 meter by 5 meter, it means if we calculate area, it means there are 25 cells in 5 by 5, while in of having a size of 1 by 1. So 5 by 5, there it will consist of 25 cells which has dimension of 1 meter by 1 meter. So if it is 1 meter by 1 meter cell, it is going to take lot of space whenever in memory and the hard disk, but its data, its display will be marvelous. and you can show very crisp and clear, better quality picture if you have density of meter by meter or even foot by foot. So the number of cells increase in a certain specific area, the density will be clearer and clearer. However, the longer it will take to process it, because you are overloading the system, computer system, and it is processing time, memory time, so it will take more time for the processing. That's why whenever you run an operation on digital elevation model and you calculate the time, currently now we might not feel that way because the computers are very fast, even laptops and all other computer on the our table. But 20 years ago or maybe 25 years ago, it was very slow. You start the operation and then you go and have your lunch or dinner and come back. Hopefully it will be done, or it will be still working on. Thank you. Again, we are still working on the raster data. Cell values can be positive or negative. It can be integer or floating point. Especially like temperature, it can be 98.6. So how to cover it? Floating point will take more space. Integer values are best used to represent categorical discrete data, and floating point values to represent continuous surface. The location of each cell in a grid is defined by row and column, and it provides its location within the raster matrix or the graph paper, you can say. Essentially, the matrix is represented by Cartesian coordinate system. You are very well know about Cartesian coordinate system. You have done it since your metric and onwards, in which the rows of the matrix are parallel to x-axis and the column to the y-axis of the Cartesian plane. Row and column values begin with 0. Sure. Now, Cartesian coordinates on our left side. 0, 0 is an extreme left bottom corner. There is 0, 0. Y-axis height is 0 given, and the width is 0, and the xy coordinate, he is talking about the cell number 5 and 1. So the red arrow is going there. So this, under Cartesian coordinate system, 5 and 1, 5 shows x, 1 shows y. Now, in UTM projected coordinate system, how we were going to do it? So, north and east, this is same thing, coordinate at 3500 east, and the north is 5960, sorry, north. It is in, maybe it is in not degrees, but all the coordinates are given. Let us say it starts from left, extreme left corner is 300,000, and the extreme right x-axis in the east-wise is 300,000 and 700. So this is the way they are writing. Point density. This calculates the magnitude per unit area. So how we can say that this map is denser than the other one. Its density is higher than the other one. So its magnitude per unit area from point feature that fall within a neighborhood around each cell. So see here the blue one, the middle one, it's either it is going down or it is the highest point of a hill. And if we go the bottom number 795600, maybe it is surface elevation. And on the other side, the next one, which is not green but between green and this, it is 3221400. Now it is less or maybe high, and then again 1960400. So the height is increasing. Maybe the middle one, it is like a very high hill. So this shows this is some sort of a digital elevation model, or you have done your survey of the hilly area and you have developed the contour lines, and this, so it is showing the neighborhood that way. Now whenever we convert data from regular map G sheet of survey of Pakistan and then you develop it into vector format, or it is in scan document, you can say scan is some sort of raster format. But let us say if you have vector and now you want to convert it into raster, then this conversion process is, yes, of course, tedious, but it doesn't mean that it will be, the conversion will produce exactly with all the geometrical shapes, areas, lengths, it will maintain everything. I doubt it. It cannot. Whatever we attain in one, when we converting into the other format, we will lose always something. So whenever data is converted from raster to vector or vector to raster, data will surely get degraded by some amount. Sure. Issues related to degradation include loss of detail. Whatever detail you have seen in G sheet of Bahawalnagar or Islamabad, while we convert it into raster or into vector, it's not easy. Lot of detail will be missed. So that's why 90% of the cost is to develop the data. Software is already done with. It doesn't. You don't have to. If you have to buy, you don't have to put too much money. Maybe 1 crore, you can buy ArcGIS, all the tools with it. But when you have to develop the data of one city or one, let us say Punjab, maybe you need 1 billion rupees to develop it. Loss of accuracy, surely the data conversion, the location of certain points are get messed up. Stair stepping raster to vector, whenever we convert or back convert, and then there will be accuracy will be being compromised every step of the way. Changes to the original data. So original data, whatever we have in G3, we feel that it is the correct data, and you will, whenever you develop that data and then you convert from one for JPEG to .mbed, .rtf, all those are different type of rasters. So whenever we make changes, be sure that compromise accuracy is being compromised and some details are being messed out. Choosing between data models, raster or vector. Raster might be faster, but vector is correct data. This is a common saying in GIS. You will use it in your life also. So further details why to select one model than the other one. Raster data is useful when working with continuous data types, elevation, slope, satellite photos. So this type of data, all data coming from satellite, hills, slope of the hills, elevation, digital elevation model to show your surface of your field or surface of a terrain or surface of a dam. We need raster. Good for large area analysis, good for surface analysis, mathematical modeling, spatial detail isn't important. So mathematical modeling are good for surface analysis, good for large area analysis, mean we have to develop a dam and we have to develop a digital elevation model. We can find out very easily which area will get impacted or not because we know through digital elevation model the top point or top elevation which we'll select, which after making the barrage or the gate or the spillway, we will know this is the maximum point where the water will be stored. So we can then find out the hydraulic gradient, that hydraulic grade line, that how much, what will be the size of the water going backward. Will the city like let us say Nushaira versus Kalabag Dam we are making or we will make inshallah. So how to make use of GIS to interpret the data, whether the Nushaira will get some sort of risk from the construction of the Kalabag Dam or not. It can be done very, very easily by DEM through raster. Vector data is useful when working with discrete data types, trees, buildings, property boundaries. So whenever there is a fixed boundary and thin lines, so at, we have to count, let us say, tree only, then or only small houses, let us say. So vector data will be very good because one house, we want to calculate the area of a house. If a house is, let us say, 200 feet by 200 feet, maybe it is 5 marla. Now 5 marla to show in Google Earth is very difficult because the cell size, pixel size is 30 meter by 30 meter. And whenever you go down to look at your gate or door through Google, you will see that the map will be ruptured. You cannot see anything. So that is the whole difference. So you need density, but this type of maps, housing, boundaries, the vector is always the best one. It is good for small study areas. Spatial detail is important. When close enough isn't really good enough. See, spatial detail, if we want to develop our boundary between India and Pakistan, let us think, our district boundary, or our acre with respect to other person's acre. With vector data, with proper survey and vector data, you can do it ideally. 100% accuracy can be developed as long as your GPS is good, your total station is good, Your conversion from GPS real life into ArcGIS is good one. You don't compromise anywhere. You will see the quality of outcome by vector will be the best one. Same thing goes for when topology is needed for this analysis. If we want to know who is on our left side, who is on the right side, like Nadra a case I used to tell you, or let us say if voting rights, let us think that way. So, or you want to develop some sort of a tax base. So, we need the house numbers. The houses which are going are located on the back of our house, and then in front of your house there is a road, and then there are other houses. So the vector data will is has the capability to know all around all the areas which are lying around your house. That is due to neighborhood analysis, contiguity, adjacency, and area representation. All those three things which I taught you earlier in the book when we were reading in the textbook. So, vector has that capability. But how much water will be stored, water will flow backward or not, which area will come under the flood, or how much excavation I have to do, because when I am going through certain area for the road construction, this will be done by digital elevation model, which is in raster format. Thank you. Yes, sir. Previously, there was one mistake which I have to redo some work. That's why there was a difference. Anyway, the conversion of models. Following are a few examples of tools which we use in our GIS to convert from raster to, especially if they are points or polyline or polygon, and it can be converted into other kind of data format and within how many types. Let us say raster to point, it is only one raster to point. And the second one, or the lower one, raster to polyline. This is the line. Contour, stream to feature, raster to polyline, cost path. So this is different type of data which we need. Although we will show the contour will be shown by a line. It is polyline also. Stream or to feature, or raster to polyline, or the path, how much money which we will spend going a certain way. So that is also some sort of a, we have to create some sort of a direction. That is polyline also. Raster to polygon, the area one. So view sheds, watersheds, raster to polygons. So it means these are, if there is a one point and we have to find out how much water will come down to that particular manhole, let us say, or water is coming from one hole, let us say our Westwood colony, and then it comes to only how much water will come down to Raven Road or to other manhole which we have developed. So this is raster to polygon. Okay, point to raster, interpolation tools, kriging, splines, density tools, they come point to raster. Polyline to raster. This is also data conversion. Polygon to raster. Polyline is different, polygon is different. Polyline has a length only, while polygon has area, that is whole connected with area. Again, we are showing various kinds of digital elevation models. Resolution 30 meter is the same area, but the pixel size is 30 by 30, 30 by 30, which you are using, let us say, under Google Earth. Or if you go on the net and you try to find out the free without making any payment, uh, most probably you will get 30 by 30 size pixel of the digital elevation model of Pakistan or America. Now the next one, the right side or middle one, is now it is clearer with respect to the left side 30-meter digital elevation model. Now if we go exactly to the extreme right, this is 3 meter, 3 meter by 10 feet, 3 meter digital elevation model. Now here you can find out, you can look down very clearly the deep valleys or deep streams, or maybe the black areas, the high hill, top of the hills, or maybe it is the deep down. It is some sort of canal system, not canal system. The stream system is being developed. Or look like you are working, going on GT road, and you are looking at Potohar area. So those earthen hills look like this one. But main thing is there is a more clarity, because 3 meter by 3 meter pixel will give you reasonably good idea what type of terrain you are working on. This is from the textbook. Digital elevation model are generally 30 meter, 10 meter, 3 meter and 1 meter. Now 1 meter is very costly. We will not be able to find out that easily from the free market. You have to buy it from Sparko, and Sparko might ask you several questions why you are interested in 1 meter, because the defense agency comes in that why you are asking for so, I mean, a higher density, because maybe it is a, what is against the, it is a security threat. So that is the reason. But even if you have some friends in with the European Union or in India or China, and you can talk to their main suppliers, but they already have done under international protocol, they have made agreements with every country. Whenever they will give this type of 1 meter or maybe 2.5 or 5 meter even, they will ask the defense agency or defense forces of that country, whoever will be the representative of that country. Our Sparko is part of the defense forces. So only they have the ability or the authority to buy the major types of data. The 30 meter and 10 meter DMs are United States DMs. The 3 meter DM is a derived product from LiDAR data. So it means the USGS means that satellite is working. So that is giving enough 30 meter or 10 meter. It is using 30 or 10 meter wide pixel, but if they can interpolate and they have a LiDAR system, maybe then that data will be coming. But I have already explained you that now there is a resolution of 62 or 82 centimeters. I mean less than 1 meter resolution is available now, and it is being sold in the market. Only we have have to have the capability or the authority to get that type of data. Thank you. Types of raster data. Satellite imagery, which we get it from various satellite companies, NASA, French, Chinese, Indians, even now Japanese. And then we use software, ARDUS, and you use it through Sparko, and we can get all this type of satellite imagery in Pakistan. Our other country, it depends on the size of your pocket, what type of data you are using. Now, number two is a digital elevation model. It is about the elevation of the surface. If you have run the survey on each square foot or each square meter or each, let us say, 10 meter by 10 meter, and then you make its 3D surface, it will show some sort of a digital elevation model. And if you use it, because DLG file, it can be, or DRG data format, it can be converted into GIS file. It depends. You are using raster GIS, or you are using vector. It used to be separate. First it was like ArcView, it was totally raster format, while the ArcInfo, this was working on network system or bigger computers. But now that after 9.5 actually, Arc 9.5, then, and the powerful computers have also been manufactured. So now both have type of, raster GIS or vector GIS, they have been converted, and now it is Arc 10, Arc 10.3, Arc 10.5, where both type of data can be displayed at the same time, and you can conduct the spatial analysis also. Digital orthophoto, these are the basically pictures which are taken from different angles, but mostly it is aerial photographs. Land cover data, so it can be regular maps, and then they have been scanned one way or the other, and we can get the most of the features of on the top of the earth surface. It is a forest, or it is a mining area, or it is a water bodies. Those can be shown on the cover data. Bi-level scanned files, the same type of land cover data, but this is a scanned document which we do it all the time in our university. It's the same thing, only maybe the system GIS will not be able to work on it, or it will not be able to negotiate with it because it is a passive. But if we develop its attribute table with it, then the system or GIS can talk to it, negotiate with it. Digital raster graphics, DRGs, it is same like DEM or scanned and graphic files, sorry, which we do it mostly in our paint shop, or so JPEG or that type of bitmap, .bmp, RTF, all those files are graphic files. Now, GIS software specific raster data. Some of the data, like we will say that if it's coming from Sparko without using ERDIS, we will not be able to use it for GIS spatial analysis purposes. It means the some work has to be done. So this is this is for this sake that all the data, whatever we have from satellite or aerial photograph, it has to be converted in one form or the other, which is which could be understood by the specific GIS which you are using. Sometime we are unable to convert it into a format where your arc 10 or arc 5 will be able to take in, like AutoCAD, let us say. Sometime if you save it in some JPEG format or other format, maybe, otherwise AutoCAD directly drawing, sometime they cannot come down to word format. So that he is trying to explain, maybe. Thank you. Previously, we were discussing about the raster data produced by satellites and supplied to Pakistani community or scientists through the Sparko. And there are vendors in the international market or the people who are producing in a private sector with and governments of the world, Chinese or government, same goes with India, NASA also, European Union also, so and Russian is also now in the market and they are selling. So Econos and GeoI, QuickWord and WordView. So these have panchromatic also and multispectral also. Panchromatic, mostly it can give us from 82 centimeters to 65 centimeter in QuickWord case, while multispectrum is the lowest one in panchromatic is 41 centimeter, and while multispectral is 1.65 over 1.85. So these are the smallest grid size which can be given. That is 1.65 is around maybe 3 feet plus minus. So we can have very significant accuracy if we utilize these ones, especially for water resources and even for the road design and other irrigation purposes for the new area which has to be irrigated and canal has to be developed, are the areas which can be flooded. So these multispectral 1.65, especially if we get this one and the crop for the sugar cane or the cotton and all those crops, we can significantly correct measurements can be ascertained. Thank you. Digital elevation models. In my research in 92 to 95, I have used it at that time for developing the flooding area at certain cities, and so that's how I feel better off with this type of raster data. A digital elevation model consists of an array of uniformly spaced elevation data. Digital elevation model is a 3D representation of a terrain surface, commonly of a planet, moon, or asteroid if you want, and maybe one fine day you will definitely use it. Created from a terrain's elevation data. A global DEM refers to discrete global grid. Basic method for producing DEM is to use a stereo plotter and an aerial photograph with overlapped areas, and a 3D model is produced and elevation data is compiled by the compiler or the GIS expert. There are the new technique which has come up. If you go in the internet and get the DEM or the digital DEMs coming down with the ARC 10 or S-series free data, mostly those data are 30 by 30 pixel size. But if you are ready to make the payment, or if you are your client who is going to get the research are going to uh, is asking you to design certain areas for irrigation or roads or railways, then we have other sources to find. LiDAR, light detection and ranging, is a new technology. The ranging technology is used also in our GPS because it finds the distance from wherever the signal is coming from the satellite and the GPS receives it. So this ranging is a new technology for developing digital elevation model. The basic system includes three things: laser scanning in an aircraft, it is already fitted in the aircraft, GPS, and an inertial measurement unit. It can create high resolution DM with a spatial resolution of 0.5 to 2 m and a vertical accuracy of plus minus 15 centimeter, which are georeferenced already. Thank you. As I have talked several times about ERDAS, Earth Resource Development Assessment System, which converts satellite data into readable format for GIS use. This is a digital image processing software used for study and analysis of satellite imagery. It empowers to collect, process, analyze, and understand raw geospatial data, and ultimately it delivers usable information. This software provides true value, consolidating remote sensing, photogrammetry, LiDAR analysis, basic vector analysis, and radar processing into a single product, incorporating the following standard enterprise capabilities and product. 1. Image analysis, remote sensing, GIS. It supports for optical, panchromatic, multispectral, hyperspectral imagery, radar, and LiDAR data. Spatial modeling with raster, vector, point cloud operators, as well as real-time results preview. High performance terrain preparation and mosaicing. Ability to convert more than 190 image formats into all major file formats, including GeoTIFF, NITF, CAD drawings, JPEG, JPEG 2000, ECW, and MRCID. Thank you. I wanted to explain you also about the ARDAS and ArcGIS, how they are similar or what one can do for the other. ARDAS is a digital image processing software used for analysis of satellite imagery. It can be used for extraction of digital number values of pixels, which we have already done it, that each table, each grid has x and y starting from the top 0 and its value. Import, export raster and vector satellite images. Combine various bands of satellite imageries to perform detailed analysis of various objects and information using the pattern recognition technique. So it has some sort of statistical analysis tool in built in. Everything on ERDAS has a unique concept of visual interpretation of satellite imagery, while on ArcGIS, its proprietary software by ESRI generally utilized for mapping various geographic features on the Earth as raster and vector data. GIS helps in effective data management where it can map various kinds of data along with their attributes. Tasks like mapping of roads, building facilities like ATM machines, location, restaurants, hospitals, clinics can be done using ArcGIS. If you want to find out the shortest route for a hospital or a restaurant or using Cream or Uber, you can use this tool to find them out. The backend algorithm, JavaScript, and Python gives you the output. Thank you. For a country like Pakistan, most of the data definitely coming for elders are is mostly comes under survey of Pakistan, which is a defense uh, defense related organization. Uh, I'm just trying to show you guys how the digital elevation model is utilized for the Islamabad Rawalpindi, and it is a 90-meter digital elevation model, and variety of digital topographic map data and satellite imagery are available in Pakistan. Bathymetry and vector layers such as contours, hydrology, and roads in industry and used by NESPAC and other consultant and NHA especially. And the file format, whoever is using these imagery, definitely he that company is also going to use ERDAS and ESRI, and that the formats it will be in .shp shapefile, DXF or DWG, and .dem a digital arc ARC is for the arc info. So these are the formats mostly available. I mean, you can buy these software already for certain areas in Pakistan, and also as well as satellite imagery in high resolution satellite imagery, ECNOS, QuickWord, Geo-1, World View 3 of Pakistan. So there's some people they are selling it. So it is not that we are going to just visit this type of technology for the first time. No, it is being used around 2025 since the last 20 years in Pakistan, while in America it has been going on from early, I mean 1990 to onward. But by the mid of or by the end of the previous century, then it has been most of the data of Europe and America has been developed in the last, especially between 1990 to 2010. So these data in cell size 5 meter, 2.5 meter, they are available in Pakistan on very comfortable rates. So try to, whenever you have your next project for the overall class after one year maybe, so try to use this map which I am showing you on the left side of this presentation, and especially Abbottabad area, Islamabad Pindi area, or Attak area. Other maps you can always get it, and we can easily find out the small streams. You can find out the 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 ponds, or maybe lakes, or maybe it is the Islamabad Dam. So it will be better if you use this one for your project, and we can find out the overall capacity of these small branches, or the, I don't want to say Ganda Nalas, but whatever Lay Nala is over there. So to find out its capacity, etc. Thank you. Ladies and gentlemen, again we are talking about this G sheet issued by Survey of Pakistan. This is about Islamabad and Rawalpindi area. I have written that clearly this longitude 7302 and latitude 33.25 minutes. The starting point is on the extreme left corner, and the total distance covered in minutes is 15 minutes from extreme left point to the extreme lower left, and same goes on the vertical side y-axis. Also these are the latitudes, and also this is 15 minutes. So this is actually, we don't know in this because this is not very clear, but maybe you guys have a good vision, and you can definitely look through it. Otherwise, uh, I'm going to give you at the start the site where you can find almost all the maps done by Survey of Pakistan and stored by Massachusetts Institute of Technology, MIT, USA. And you can all, I got my Bahawalnagar area, Gilgit area, all those areas I was able to find out, and you can check it. They are starting from the last one which I saw. It is in 2004 or 5. I mean, which is very recent, just maybe 10-15 years old. Although the one which you guys have seen in my office, that is in 1937. So this one which I'm considering now, Islamabad Rawalpindi 90-meter DEM, this is digital elevation model, and you can see maybe the Rawal Dam, the left, right, no sorry, right upper corner, maybe this is, or it can be the other one near Haripur, but I think it is in Islamabad and Rawalpindi area. I'm sure that this one is the, I mean, Rawal Dam. So you can see the hilly areas, the the higher mountains where there is a, I mean, yellow color. So maybe it is a flat area. So these different area which have same type of heights, so they have the same color. So this depicts the digital elevation model for Islamabad and Rawalpindi, and please find out the digital DEM for your own area, for your own district. Definitely you will get it. Thank you. In presentation number 20, I'm looking at the G sheet of Survey of Pakistan for the Bahawalnagar area, and it is 44/G2. If you go, actually it is difficult to show it, uh, speak and read it because the system is unable to enlarge the area. But if you will go down in the extreme left bottom corner, you will see there will be longitude is written, the starting longitude, starting latitude. It is written 73, that is longitude. And if you go toward right side, the at the end it will be 15. So this whole area is for 15 minutes, 15 minute of the angle. And same thing if you go from extreme left corner and you go all the way up, extreme left, it will be written maybe, I'm not sure, but maybe it is 24 or 26. And then again it is at the top, there will be 15 minutes. So this whole map is 1:50,000. This is the scale. One centi is showing maybe 1 kilometer, but I'm not sure because you will find it. It is written over there. And my village is not shown here because the next G sheet exactly left to it, that will show my village 26/3R. It has gone up to 25 only. So it means I have to find out the next G sheet, which will be G1 or G3, and that will show my village also. But what I'm trying to show you guys, actually, the whole thing was that from this type of map, we have to digitize it. This is a passive map and it is not vector, but we can make vector map from this very G sheet. And this is some sort of, it is a scan document, you can say. But we have to convert it into a digital elevation model, or which was just previously in previous presentation about Islamabad and Rawalpindi, that has been developed in digital elevation model, and you can get it of your own area. Ultimately you are going to get some sort of assignment of your own area, download it and convert it, or get it converted, or get it ready for the digital elevation model of your area. But this is the first map always you guys will use in your life. These maps are with the Survey of Pakistan. You can make the payment, you can get it, or you can go to the internet of this site on the right side. This is a dom.mit.edu. This is American University. Almost all of our Pakistan is covered in it, and you can download the area, the G sheet which shows your village or your in the area where you are interested, or you are going to make some sort of a project in the future. So what I wanted to tell you, that is a 15-minute by 15-minute each G sheet, and there will be one area will have 4 sheets, G1, G2, G3, G4. It is one quadrangle, but if you will open it in a bigger size, you will see there will be 9 squares on the bottom, and it represents one of them. Thank you. We were discussing in the previous presentation that uh, how to get the map from a regular map, then how to digitize it or convert it into a vector, and then how to further model it into some sort of digital elevation model or raster data. This this presentation is regarding conversion between two datas. And this example is about a watershed, about a catchment area, and it is represented in vector shapefiles. On the left side, it is represented in vector shapefile .shp, because you haven't done the full work on your regular lab work. Otherwise you will know .shp. It shows the vector data shapefile with it will be a .shp. The ArcGIS will convert feature to raster polygons to raster polygons. So if you have some sort of data which shows some sort of elevation, either you have done by GPS survey or regular levels, and then your total station has developed the format which is given on your left side, and now we want to convert it into digital elevation model so that we can find out the total flow runoff. So the image on the left side looks very similar to the one on the right side, but on the right side watersheds are shown in raster. They are in digital elevation model. That is the main difference. Data storage of two kinds: vector data format and other is raster data format. And the vector data format is shown in discrete representation of reality, which is, let us say, L1, L2, L3s are the parts of the cable or the road network or the bridge network going on, and where the number 1, number 2, number 3, number 4, either they are the poles of a bridge, piers, and they can be electric poles, and N1 and N2 can be the cable length from one pole to the other pole. So these are all, they are discrete elements, but it is a vector format will be shown in this way. And you can see on your right side the road is going and the bottom one, the raster format, this reality is represented by making graph paper, small square cells pixel to model the real life. Now on vertically there are number of rows 1 2 3 4 up to 10 20, and the bottom the number of column key upon exceeding. So wherever is the location of L1 L2, all the line is subsequently going adjacent to one cell, other cell, other cell. So they keep on going, touching each other. This is some sort of line is developing. Now, what in the red one, whatever you are seeing, it doesn't show that this is the width or this is the cable. This is one way to show. Now it is represented in two rows, while it can be represented in one also. But how to represent one other type of cable which is bigger or smaller, then that's why we are trying to show it that its width, this kind of cable is covering, the width is 2 cells, but they are not cells in reality. They are not showing. In reality, it is 30 meter by 30 meter. It means the width is 60 meter. The cable cannot be 60 meter diameter. I mean, even big pipeline can be 60 meters. Maybe it is a canal. It can be. So, but this is one way to show it. This is the major difference. While in case of vector discrete elements, there will be thickness of the, the lines. But if you want to show smaller canal, then other is bigger canal, and other is very larger canal, you will show it by colors only. Various colors will show the various width of the road. Otherwise, you cannot show really that it is 20 feet wide, it is 30 foot wide. That will go into the attribute table which we just studied previously. Now, if you see discrete representation of reality, and reality is on your right side, the highway, a highway. So the curving highway, and if you see the upper vector format, that bridge and 1, 2, 3, 4, this is nearly showing the same real life in vector format. Thank you.